taking a look at our homework over the weekend. Worksheet number 4. We had questions 4 through 7, I think it was. 4 through 8, yeah, through the end of the worksheet, whatever that was. Okay, 4 is up there now, 75.1 meters per second, 62.6. Number 5, take a look at the answers here. We'll take a look at maybe one of these questions before we do our quiz here today, okay? Don't panic about the solutions here right now, just look at the answers. Number 7 up here now. And finally, number 8 there. All right, request to do question number 5 here. It says a bomb sitting at rest on a table explodes into 4 pieces of equal mass. This is good. I like seeing equal mass. Okay, what are you thinking right away when you see that 4 pieces of equal mass? Probably going to cancel. We want to make sure as we're going through this that in fact I can cancel because it appears on both sides, or that 0 appears on one side. But I think that's what's going to happen for me here. Okay, it's going to save me a little bit of work on my calculator. So here's my explosion point. The first piece travels at 55.0 meters per second to the south. The second piece travels to the west at 80 meters per second. The third piece travels at 30 degrees west of north. West of north would be this way. And this would be 40 meters per second. We're going to call that piece number 3. Oops. Label it as 40 meters per second. And where do you think piece number 4 is going to go? I know one way it's going to go for sure. We know it's going to go to the left for sure, right? Has to. Because if we have momentum, sorry, to the right, I mean. If we have momentum to the left due to object 2 and 3, then we have to have momentum to the right due to object number 4. Now, is it going to go up or down? That's a tough one. We don't really know by looking at this question whether it's going to go up or down. So it's going to be a bit of a guess. Okay, I'm going to guess that it's going to be this way. Object number 4 is going to go this way. But in the end, like we've said a million times before, if we guess wrong on the piece that we're trying to solve for, it's okay. We only draw that to visualize it anyways. The important ones are the blue ones. We have to draw those correct because those are the ones for which we've been given data. We've got to get those right. Okay, the red one, it helps us if we get it right. It helps us to visualize it, but it's not the end of the world. All right, I see one funny angle there. And what's the first 5 words that come to your mind when you see a funny angle? I don't like funny angles, so let's get rid of it. Okay, let's take it over here. Let's redraw my funny angle here at 30 degrees. This would be the x side. This would be the y side. And my hypotenuse would be 40 meters per second. The x side is the opposite or adjacent side of the triangle. Opposite, so it's going to be which trig function? Sine, cos, or tan? Sine. Let's say sine 30 degrees is equal to opposite over hypotenuse. So x is going to end up being 20.0 meters per second. The y component is therefore the adjacent side. We're going to use cosine for that one. Cosine 30 degrees is equal to adjacent over hypotenuse. And y is equal to 34.6 or something like that. 34.641. Okay, so what I can do at this point, if I want to, I don't have to, but I can replace this with a vector that goes up this way at 36.641 and a vector that goes this way at 20.0. And now I don't have any funny angles. Some people look at this and say, well, vector 4 is at a funny angle. Yes, it is. Vector 4 is at a funny angle, but I don't know what that is. That's what I'm trying to find, so it doesn't really count. I don't worry about it if I'm trying to find a funny angle. That's easy. It's only if I have a funny angle that it creates the problem. So all the problems are fixed here now. Let's go into my x components and my y components and treat it just like one of those T-bone collisions now. Say for the x, pi is equal to pf, of course. The initial momentum is 0 because it's at rest. If this bomb was moving before the collision or the explosion took place, then we just have a term in there, right? mvi. Okay, and m would be the total mass. Vi would be whatever the velocity of the bomb was before it exploded. Okay, it's not moving, so the initial momentum is 0. m1 v1f plus m2 v2f plus m3 v3f plus, for the first time I think this year, m4 v4f. Now, odds are on an exam this isn't going to happen, but conceivably it could be m13 v13f, right? Okay, that's a lot of work, so you're probably not going to see that, but it doesn't matter how many objects we have. We just put a term in for each one of them. Masses do, in fact, cancel because the masses are the same and 0 appears on the left side. v1f is 0 because it's moving straight down. None of it's on the x component. v2f is negative 80. v3f is negative 20. The x component is neg 20. Plus v4f. So we're going to say that v4f is equal to, take these over to the other side by adding, works out to be positive 100 meters per second. Did we guess right that it's going to the right? Yeah, we got a positive number for v4f, so it's going to the right. Okay, that's the one we knew, though. That wasn't really a guess, right? We knew it was going to the right. The guess was, is it going up or down? So here's our test right now to see if our guess was right. Pi is equal to Pf again. The initial momentum is once again 0. Masses cancel again. This time V1F, if we look back at our diagram here, V1F would be negative 55 because it's straight down. V2F would be 0 because it's only on the x component and we're dealing with the y component now. V3F, if we look back to the green there, positive 36.641 plus V4F. Neg 55 plus 36.641, that's going to give me 18.359. I'm sorry, what is it? Yeah, actually, I think it was, yeah. 34.641, thank you. So that's going to give me 20.359. And it's going to be negative on the right side. Take it over to the left side by adding. What did I say? 0.359. Did I guess right? Had I guessed right that it was going right and up? Yeah, I did. It was maybe 60-40 guess at best. So it was really kind of a guess that it was going up. Okay. We knew it was going to the right. We guessed that it was going up. We guessed right. Okay, great. Okay, if we hadn't have, no big deal. Let's combine them now. This is the easy part. This is the physics 20 part, right? We got 100 to the right. We got 20.359 up. And we're going to combine them like this using the Pythagorean theorem and the inverse tan function. Any troubles with that? Okay, make sense? Yep. Okay, let's go through that right now then, okay? The inverse tan theta is equal to the inverse tan of opposite over adjacent. And the opposite side of this triangle is which side? The angle is always drawn at the start, okay? That's where you see no arrows, the start of the diagram, okay? Of course, my result is drawn from start to finish here. Okay, so my angle is always drawn right there at the very beginning of the picture. Which side is opposite to this angle? Which side is not touching this angle or not adjacent to this angle? Yep. Which one? Yeah, 20.359. Good. So the adjacent one is the one that's touching, and the opposite one is the one that's not touching. Make sense? And the angle, I mean, the key is getting the angle in the right place, right? It's always drawn at the start of the diagram, from start to finish. Okay? You good at that? Patrick? The answer to number 6 was 103 meters per second at 19.0 degrees south of east. I'm sorry? This one was number 5, I think, wasn't it? 102 meters per second at 11.5 degrees north of east. Let's take a step back for a week here or so now. You guys remember a while ago we talked about elastic versus inelastic collisions. We talked about those in the context of one-dimensional collisions, but we can extend that to two-dimensional collisions. An elastic collision, it was a collision in which what was conserved? What stayed the same in an elastic collision? Yep. Good. Momentum and kinetic energy stayed the same. An inelastic collision was a collision in which momentum stays the same, but kinetic energy was lost. We never found that kinetic energy was gained, right? Not in the context of a collision. Okay, an explosion, yes, but we don't define those as being elastic or inelastic. So inelastic, kinetic energy is lost, momentum stays the same. Now, when we calculated the initial and the final kinetic energy of all of those objects, we would say maybe EKI is equal to 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared, and so on. We would calculate the final kinetic energy. If there was two objects, once again, it would be 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. There were a couple things that we pointed out that you had to pay really close attention to and to be careful of. The first one was, even if the masses were the same, you couldn't cancel them out. You couldn't cancel them out because they didn't appear in every term. If M1 was 20 kilograms, M2 was 20 kilograms, that's great. But that 20 kilograms doesn't appear on the left-hand side. So you can't cancel the mass out, even if it's the same like you can in conservation of momentum. Now, the other thing was this. You guys remember, if, let's say if one of the objects, let's say object number 1 was going to the north at 20 meters per second, which we would normally make a positive 20, right? Object number 2 was going to the south at 15 meters per second. We would normally make that a negative, right? In this case, we dropped the sign of the velocity. Why did we do that? Why did we not pay any attention to the fact that the 15 meters per second was south? Patrick? Good. When we're doing conservation of momentum, as we just did in the quiz, when we're doing conservation of momentum like we've done for the most part in this unit, we had to pay attention to the negative. But when we're doing kinetic energy, we don't. Not only do we not need to pay attention to it, we shouldn't pay attention to it. Because it's not velocity here, it's speed. So in conservation of momentum, this would be a positive value, this would be a negative value. In kinetic energy, right, elastic and inelastic collisions, this would be positive, this would be positive as well. Okay, does that ring a bell? Hasn't been that long since we've done this stuff, right? What if we have a question like we've been doing the last few days, where a car is going to the north and another car is going to the east, or a car is going to the west and another car is going at 16 degrees south of west when they collide? What do we do now? Well, it's a two-dimensional collision, right? So we have to break it up into x and y components when we're doing conservation of momentum. Do we break it up into x and y components for this? Logan? No. Why not? Because it's energy, and energy is a scalar. Okay, do we pay attention to the 16 degrees south of west or whatever angle that I gave you? No. Why not? We don't need a direction. Not only do we not need a direction, we don't want a direction. It's a scalar. There shouldn't be a direction associated with it. So the questions that you've done over the last few days in two-dimensional collisions, we do have to break them up into x and y's when we're doing conservation of momentum. That doesn't change. But if we're trying to find out whether that collision is elastic or inelastic, then we're going to treat it in the exact same way as we treated our other elastic and inelastic questions. We're not going to turn it into an x and a y component of kinetic energy. We should never, ever do that because kinetic energy is always a scalar. Okay, it looked like this when we did kinetic energy before. It looks like this now. Does that make sense? We're going to do one question here. I was going to give it to you as a practice problem, but just in the interest of time, I'm going to do it in class here today, and that'll effectively be it for us. This one says a 0.16 kilogram, 168 kilogram hockey player flying puck. It's a puck flying, not a player flying. Players don't fly. Pucks fly. At 45 meters per second, that would be a quick hockey player too, 45 meters per second. 252 degrees is trapped in the pads of an 82 kilogram goalie moving at 0.2 meters per second at 0 degrees. The velocity of the center of mass of the goalie pads and puck immediately afterwards is this. Was the collision elastic? And if not, calculate the percent of the kinetic energy retained. Okay, we're not real concerned with this last part. We'll do it. Okay, but the big part of this question is this. Was the collision elastic or not? Now, you could probably make a pretty good guess at this right now. In fact, you could probably make 100% guess on this. Is this collision elastic or inelastic? Inelastic. Why do you say that? Because they stuck together. Right? It's inelastic because they stuck together. We're going to justify that mathematically, though, okay, just so that we go through that process of doing the math here, okay? Let's draw it out here because it's a little bit confusing with those 333-degree angles and 252. Our XY coordinate system, remember, this is 0, this is 90, this is 180, this is 270. So the first one is going at 252. First one's going down here. That's 18 degrees away from 270. Okay, so our first one, we're going to say that's object number 1. That's the puck, 0.168 kilograms, traveling at 45 meters per second. And it's going downwards this way at 18 degrees. It collides with a goalie moving at 0 degrees. 0 degrees is to the right. Okay, that's going to be player number 2. His mass is 82.0 kilograms, so dramatically heavier, but also dramatically slower, 0.200 meters per second. Now, they give me a bit of a break here in that they don't ask me to calculate the velocity of the third piece or of the combination puck and goalie after the collision. They could. Okay, they could say, is this collision elastic or inelastic, and not tell me that number. We could find that, right? We could find that by doing x and y components just like we did on our quiz, and then do the kinetic energy thing. Okay, the good news is here, we've already got it. 333 degrees is going to be down here somewhere. Okay, this is 360 right here. 333 is going to be 27 degrees short of 360, right? 27 degrees less than 360. So it's going to go down here somewhere, this wreckage. Okay, 27 degrees right here. We could have predicted that it was going to go down there somewhere anyways. So what's next? Funny angle, right? What do we think of automatically when we see a funny angle? Don't like funny angles. But here it doesn't really matter if we don't like them because we're not paying any attention to them, okay? If you're a hockey player and there's a certain team you don't like, okay, that's fine. You don't like that team. But if you're not playing that team, it doesn't really matter if you like that team or not. We don't have to deal with it. Okay? We're not playing this angle here. We don't care about that angle. It doesn't make any difference. All we're going to do here is say EKI 1/2 M1 V1 I squared plus 1/2 M2 V2 I squared. And then we're going to calculate EKF, which is 1/2 of M times VF squared. No components, no 18 degrees, no negatives, no nothing. Okay, it's as if these two things collided head on or if it was a rear end collision. It doesn't matter. It's exactly the same thing. 1/2 of 0.168 kilograms times V1I, 45. Not 45 at 18 degrees, not 45 down, doesn't matter. M2 was 82 times 0.2 squared. To the right, doesn't matter. Okay, that's all we do there. Let's calculate that number. See what we get. Say 0.5 times 0.168 times 45 squared. Let's add to that, let's do some brackets here, 0.5 times 82 times 0.2 squared. 171.74 joules, which we should actually round to 3 digits, so 172 joules. Because we want to be in the right number of significant figures so that if the numbers do happen to be really, really close, we can compare them properly. Now the combined mass here, we've got 82.168 kilograms, because the puck and the goal go off as one object afterwards. And then go 27 degrees, 0.192 meters per second. Expect to get a number that's the same, higher, or lower. Lower, right? Because we know that it's inelastic. They stick together. It's going to be inelastic. 0.5 times 82.168 times 0.192. And we get 1.51. That's lower. That's quite a bit lower, I think. 1.51. Yeah, even if we round to one more significant figure, I think we'd still find that it's a lower number. So is it elastic or inelastic? Inelastic. We knew it was going to be inelastic, right? But if the two of them bounced apart, we wouldn't know if it was inelastic. It probably would be inelastic still, but we'd have to go through this process. Okay, does this make sense? Is this hard? Well, if elastic and inelastic collisions for you the first time we did it was hard, then this is going to be hard. Okay, if it wasn't hard, then this shouldn't be any harder. Okay, the angle, drop it. Okay, whatever. In fact, you know what, guys? Listen, if you recognize that you don't have to do conservation of momentum to find the final velocity, you don't even need to draw this picture out. We don't care which way they're going. We don't care what it looks like. Okay, the only time we really care about this is if it's conservation of momentum. Okay, make sense? All right, I'm not assigning any formal homework today. Okay, having said that, worksheet number 5, it is not homework, but worksheet number 5 involves elastic and inelastic collisions in 2 dimensions. If you want to try 1 or 2 of those questions just to make sure you're doing okay with that stuff, go ahead and do that, then check them with me to make sure that you're doing okay. Okay, if not, that's okay too if you feel comfortable with this already. Okay, that's the unit. Okay, tomorrow I'm hoping to do a lab, and then Wednesday, of course, we have our unit test. Come see me for scheduled help. Come see me at lunchtime today and tomorrow, and hopefully we'll be in good shape for our test on Wednesday. That's it for today, guys. Sorry, guys, one last question just asked here that I forgot to do. This is certainly a lot less important than the first part that we already did here, but since it asks us for the total kinetic energy retained, the percent, let's real quickly do that. Okay, we started with 172, we ended with 1.51, we retained 1.51. So what percent did we retain? It's 1.51 over 172 times 100, right? That make sense? There's not going to be a question on your test on Wednesday that asks you for the percent retained. And I'd be surprised on a diploma exam if there was, but never say never, because I don't make that exam up. So, okay, in the end, okay, be careful though. I think you said 95, right? Yeah, so it's not 95. It's not 95% retained. It would be 95% lost, right? So be careful on that one. If they ask you for the percent retained, use 1.51 over 172. Okay, if they ask you for the percent lost, then it's the other way around, right? It's what would it be? 170.5-ish, something like that, divided by 172, which is going to give you the 95%. So it's going to be about 5% lost, about 5% retained, or about 95% lost. Not hard, just make sure you know what you're being asked, how much is lost or how much is being retained. Again, I'd be surprised if you're asked that anyways, but you never know.